last day meeting. And the first talk by Timon is both about verbal quandles.
I think that at least I need a clicker. And very soon I will come. Thank you. So I think I can start before my slides will show up. First, I would like to thank the organizers for organizing and for giving me an opportunity to give a talk here and to listen other talks, which are exciting and mostly clear. Not at all, but I think I will work on it. So then I would like to thank the listeners for listening. And my special greetings go to the guys who follow us in the online format. So, and finally, I would like to apologize in advance for my talk, because it will not be very difficult, so it will be quite elementary, but I'm sure that all of us, or at least some of us on the last day of the conference, feel a bit tired, and I hope that my talk will help you to relax. So it's the end of the sentimental part of my talk, and now I start the mathematical part of my talk. So the title of my talk is Verbal Quandles with One Parameter, and I would like to start from the definition of quandles. And a quandle is an algebraic system with one binary algebraic operation, which we denote by a symbol star, such that this operation satisfies three axioms, which are depicted on this slide. The first axiom says that x star x is equal to x for all elements from the quandle. The second axiom says that the map Sx, where x is a fixed element of the quandle, which maps an element y to the y star x, is a bijection of Q. So for every fixed element x of a quandle, right multiplication is a bijection of Q. And the third axiom says that for all elements x, y, and z from Q, this equality holds. And quandles first appeared in two independent papers, first by Sergei Matveyev and second by David Joyce. And Sergei Matveyev called them distributive groupoids. And this name was mostly motivated by the third axiom of the quandle, because this equality is indeed a kind of distributivity of this operation star with, again, this operation star. And the name quandle chosen by Joyce was motivated by the fact that this word didn't exist before. So Joyce just chosen the name quandle because it's short and not occupied by anything else. So the word quandle didn't exist before 1982. And now, since the word quandle is shorter than the word distributive groupoid, the name quandle is more common. So, but anyway, now we know that there are at least two names for quandles, and which appear from different papers. And now I would like to give you the simplest example of quandle I know. It's the trivial quandle, and it's defined as it is written on this slide. So let x be an arbitrary set, and on this set we can define an operation star by this rule: x star y is equal to x for all x and y from x. So, and this operation doesn't depend on y. And this quandle is called trivial, and in comparison with group theory, where we have only one trivial group, in theory of quandles, we have a lot of trivial quandles, which differ by cardinality. And if X is a finite set with n elements, then we just denote the trivial quandle on n elements by Tn. So, and it's the simplest example of quandle. I believe that it's the simplest. And more difficult and more, let's say, deep examples will be demonstrated later. But now I want to say why did Matveyev and Joyce introduce quandles? So they introduced them in order to construct invariants for classical knots and links, so they constructed a procedure how by a given knot diagram, classical knot diagram, to construct a quandle which is an invariant. So let me recall you this procedure. Let me have a classical link diagram, for example, a trivial knot, as it's depicted here. And so what should we do in order to construct a knot quandle? First, label the arcs by symbols x1, x2, and so on, xn, where n is the number of arcs, and here arcs are just connected components of the diagram. So, and we will construct the quandle using generators and relations. And what would be the generators and what would be relations of the quandle? So generators are just labels on the arcs. It is these symbols x1, x2, and so on, xn. And relations of the knot quandle would be written from the diagram, from the crossings of the diagram. So if you have a crossing like this, and if the labels of the arcs near this crossing are as on this picture, then we just add the relation x star y is equal to z. And here I would like to note that the orientation is important only on overpass. On underpass, the orientation is not important. So, and we will have the so-called fundamental quandle of a link or of a knot. And the number of generators is equal to the number of arcs, and the number of relations is equal to the number of crossings. And here I just wrote an example of the fundamental quandle of this trifoil knot. And indeed, it was 3 generators and 3 relations. What Joyce and Matveyev did, they proved that this quandle is an invariant for classical knots and links, and they proved even more that this invariant is, I would say, quite strong, but it's better to say very strong. More precisely, they proved the following theorem, which says that if we have 2 knots, by a knot here, I mean a link with only one component. So then fundamental quandles Q of L1 and Q of L2 are isomorphic if and only if L1 and L2 are weakly equivalent. It is either they're equivalent or L1 is equivalent to the mirror image of the reverse orientation of L2. So in this theorem, it's not correct for links, it's just for knots. And this theorem says that, let's say, in order to distinguish different knots, we have to understand how to solve the isomorphism problem for quandles. Because if you have 2 knots, if you want to understand if these 2 knots are equivalent, we go to quandles. We need to understand if these quandles are isomorphic or not. And of course, on the way to solve this isomorphism problem, we have some other problems. And the first problem is it's quite difficult to work with quandles. I mean, of course, the word difficult is, it depends on the person who works with it. Here, I mean that there is no systematic theory of quandles. Up to my knowledge, there are only 2 books devoted to quandles. And if we again compare it with group theory, like there are lots of books of different level on group theory, but for quandles we have a lot of papers, but only 2 books. From this point of view, I mean, it's more difficult to work with quandles. And the second, what I would like to mention is the result, which I recently found. Result from the paper of 2019, which says that the class of quandles is Borel complete. I'm not really very familiar with this terminology, but fortunately in this paper, there was also an informal formulation of this theorem. And this theorem says that isomorphism, the informal formulation says that isomorphism problem, let's say, as difficult as it could be. So for me, for my understanding, it means that isomorphism problem for quandles is like very difficult or unsolved. So, but anyway, despite the fact that it's difficult to work with quandles and the isomorphism problem is, let's say, impossible, we somehow want to use this result and want to understand how to solve the isomorphism problem. And of course, there is an approach which I will show now. So now let Q we just some fixed quandle with some nice properties. Of course, yeah, we will discuss later what are nice properties. And if we have a knot A, then we can construct fundamental quandle of this knot, Q of A. And now let us denote by home theorem Q of A Q, the set of all non-trivial homomorphisms from the fundamental quandle of this knot to the fixed quandle Q with nice properties. So on here, I mean by non-trivial homomorphisms, yeah, it's better to say what is a trivial homomorphism. A trivial homomorphism of quandles is a homomorphism which sends all elements from one quandle to only one element from another quandle. So non-trivial, it's negation of this. So and here we denote by this symbol the set of all non-trivial homomorphisms from the fundamental quandle of a knot to a fixed quandle with nice properties. So and now, if we have two knots L1 and L2, then we can find this set of all non-trivial homomorphisms from Q of L1 to Q, and the set of all non-trivial homomorphisms from Q of L2 to Q. So, and it's clear that if these two sets have different cardinalities, then these links are not equivalent. Because if these links are not equivalent, then these guys are isomorphic, and therefore these sets have the same cardinality. So from this point, knowing something about this quandle helps us to calculate these cardinalities, and then it helps us to understand if two knots are equivalent, are not equivalent. So, and from here we can say what are these nice properties of quandles. Nice properties are properties which help us to understand, to calculate this value. So, and there are different quandles, and one family of quandles which we can say that they have nice properties are, for example, finite quandles. And I want to recall you the talk of Manpreet Singh, who was, which was given here on July 5th, where he introduced the result, which says that knot quandles are residually finite. It means that there are homomorphisms from knot quandles to finite quandles with additional properties. And from this point, yeah, these quandles are, let's say, nice. But of course, there are other options, and other options for calling quandles with nice properties, and my talk is devoted to these guys. And now I will start with these other options. But before I do it, I would like to recall you the name of this conference. All you remember it. It's called Groups and Quandles in Low-Dimensional Topology. And for me, an important part is written in the first line, in the second line in our situation. Is that it's about groups and quandles. And for me, as for, let's say, specialist in group theory, it's more convenient, more comfortable to work with groups instead of working with quandles. And for me, quandles with nice properties are quandles which somehow arise from groups. So, and since now I will speak about quandles which arise from groups. And now I want to give you several examples of such quandles. And the first example, maybe the most common example of quandle, is so-called conjugation point. In order to define the conjugation quandle, we need a group G and some integer n. Here it can be integer, so I just throw positive integers. And the conjugation quandle is denoted by this symbol, conj sub n over of G. And it's the quandle with the underlying set G and the operation star, which is denoted in this way. X star y is equal to y to the power minus n, x y to the power n. And it's quite easy to check that this quandle, this algebraic system is indeed a quandle, and this quandle is called the nth conjugation quandle. In particular, if G is a billion group, then this quandle is trivial. And here I just wrote that if G is a cyclic group of order n, then this quandle is just trivial quandle on n elements. It can be any abelian group of order n. It's not very important. So another quandle which is also famous and which can be constructed by a given group is so-called core quandle. In order to define this, we just again need a group. And this quandle is a quandle with underlying set G and the operation star, which is given by this equality. X star y is equal to y, x inverse y. And these quandles are also quite famous by the fact that if we look to x star y and again star y, then we obtain x. So it means that the right multiplication on these quandles is involution, and yeah, this property sometimes is quite useful. So here in particular, if G is a abelian group, then the core quandle has a special name. It's called the Takasaki quandle. And such algebraic system appeared in this work 40 years before the word quandle appeared. So, and even more, if G is a cyclic group, then this quandle again has a specific name. And it's called the dihedral quandle of order n. So like this amount of different names of the same quandles says that yeah, different people are working with it. So I will give you a couple of more examples. And another example of quandles which arise from groups are Alexander quandles. In order to construct Alexander quandle, we need to have a group G and an automorphism of the group G, just fixed automorphism. And in the literature, I found several quandles which are called Alexander quandles. And here I depict all of them. Yeah, I will comment only one of them. So, for example, first, Alexander quandle, which is denoted by Alex G and phi. It's a quandle with underlying set G and the operation star, which is given by this equality. X star y is equal to phi of x y inverse multiplied by y. And here you can see that all the operations are pretty similar, but anyway, they're different. It's very reasonable to call all of these quandles Alexander, but they're just different, and I think it's not a problem. And here I just wrote some index in order to distinguish them. There is no big sense behind this index. Yeah, and
excuse me, what is phi? Phi is an automorphism.
It's an automorphism, but yeah, yes. So, and there are different papers where these quandles are used for constructing invariants of knots. Yeah, but first I wanted to show you these papers, but decided not to. And one more example, it's even not example, it's just mentioning that there is a type of quandles called G8 quandles. These are quandles which can be defined by a group G and an arbitrary subset of this group. These guys were introduced in our joint paper with Valery Bardakov. And they're using these G8 quandles. We've proved several results. In particular, we classified quandles with enveloping group, which is pre-abelian rank 2. I will not give the definition because it's kind of need some time and space for giving it. But I just want to say that a lot of known quandles are G8 quandles. For example, conjugation quandles, which were on the previous slide, Takasaki quandles, and some other quandles which we didn't introduce in this talk. All of these guys are G8 quandles. So and now I go closer to the title of my talk and would like to define verbal quandles. So what are verbal quandles? So let f of x and y be the free group with two generators, x and y. And let w be some word in this free group. So if you have a group G, then the word w defines a map from G squared to G, and it's quite it has quite natural definition. If you want to define the value of w on the pair of elements, just take write the first element instead of x, the second element instead of y, and we obtain an element from the group G. So now, for two elements G and H from the group G, denote by G star sub WH, just the value W of GH. So, and we have an algebraic system with underlying set G and the operation star sub W. And if this algebraic system is a quandle, then this quandle is called a verbal quandle defined by W. So it's a very natural definition. This quandle is defined by a word, W. That's why we call it verbal. Yeah, here I would say that there are other algebraic systems defined like in this way, by word in input. And what we did with Valery Bardakov and Mahian Dersin is we classified all verbal quandles. So we proved that if W is a word in the free group such that this algebraic system is a quandle for every group, then we have only two options. Either W is this word, y x inverse y, or W is equal to y to the power minus 1, x y to the power n. Yeah, and in the first case, we have the core quandle, in the second case, we have the end conjugation. So, and verbal quandles with one parameter, which are in the title of my talk, is a kind of generalization of verbal quandles. Let me introduce it. So, now we have the free group with three generators, x, y, and z. And we have a word in this group, W of x, y, and z. And now let G be a group and T be a fixed element in this group. And now again on the group G, we will define an operation by the given rule. For G and H from G, we denote by G and here star with two sub-indices, W and T, where W is a word and T is an element from G. And it's just equal to the value W of G, H, and T. So again, we have a new operation on the group G. So it's an algebraic system with one binary algebraic operation. And if this algebraic system is quandle, then we call this quandle a verbal quandle defined by a word W and an element T in G. And this quandle, yeah, it's called verbal quandle, but I would say it's verbal quandle with one parameter because T is kind of parameter.
But it is fixed for one quandle, it is a fixed element.
Yes. Yeah. So, and let's say the main result which I wanted to show you here, I mean, it's not very difficult, but yeah, I wanted to give a story around it. Is this result which we obtained with my student? It's the classification of all verbal quandles with the one parameter. So let again W be a word and free group on the three generators, and this word be such that this algebraic system is a quandle for every group and every fixed element in this group. Then W has one of the following forms, and there are only 6 of them. You already saw these two words. It's just here we have core quandle and we have conjugation quandle. And these guys, 4, are Alexander quandles. And if you remember, in the Alexander quandle, we had an automorphism phi. And in this case, an automorphism phi is just inner automorphism, which is conjugation by the power of n. And nothing more can appear in this situation.
Is it Z is T here? Is a typo?
Again, please.
There is this parameter Z here. I guess it is the T one.
Here we have the word W is the word in 3 generators, F of X, Y, and Z. Of course, when we define the operation on the group, then we write T instead of Z. You see here we have W of G, H, and T. But for the formulation, Z is correct. Yeah, and Mahendra, I hope I answered your question.
Yeah. Okay. Thank you.
So, and where can we need these quandles? And one opportunity where we can need these quandles is for constructing new node groups. And let me show you how to do it. It's quite easy. If you have, for example, a classical node diagram. Then we can construct new node groups defined by these verbal quandles. How to do it? First, we label again the arcs of the diagram by symbols x1, x2, and so on, xn. In our case, there are only 3 labels. And then we define a group, which we denote by G sub W of A, where A is this diagram and W is a word from the formulation of the theorem. How will we define it? We will define it by the set of generators and the set of relations. Generators here are x1, x2, and so on, xn, and an additional generator t. So these guys are labels on the arcs, and t is always a generator which we will have for all nodes. And what would be relations? And relations would be written from, again, from crossings. And if we have labels on the crossings, and as it's written here, then the relation will be like this: W of x, y, and t is equal to z. So t will exist in every relation. And for example, in this situation, we have a group generated by 4 elements: x1, x2, x3, and t, and 3 relations which are written here. Of course, W is not just an arbitrary word. The word W is from here. We have these options. And somewhere at this moment, one can say that why should we need these groups? Because in classical node theory, we already have the fundamental group of the node, which first doesn't have an additional generator, which has less relations, less generators and less relations. And it's strong invariant. Why should we need it? We don't need it in classical node theory. However, in virtual node theory, there are no natural definitions of groups, and we can use it in virtual node theory. And before giving it for virtual node theory, I would like to recall you what is virtual node theory. I mean, not in details. I would just say that virtual node theory was introduced by Kaufman in this paper in 1999. And virtual node diagrams look similar to classical node diagrams. The difference is that there is another type of crossings called virtual crossings. And there are also Reide-Meister moves on virtual node diagrams. And these guys are just look like this. So these are examples of virtual node diagrams. I will not show what are Reide-Meister moves, just, yeah, would say that it exists. And if a diagram doesn't have virtual crossings, then it's just classical node diagram. So, and using this verbal quandles with one parameter, we can construct new groups for virtual node theory, which are invariant. And now it becomes important because there is no natural definition of a group. Of course, there are different groups defined in virtual node theory, but like they have different motivation, and none of them are, let's say, natural. And here we do the same. In order to construct a group, we label the arcs by the symbols x1, x2, and so on, xn. And here by arcs we mean paths from one underpass to another underpass. We just ignore virtual crossings, and then we write a group with generators of x1 and 2 and so on, xn, and an additional relation t. It's completely the same as in previous case, but the definition of arcs is different. And here, of course, one can ask about verbal quandles with n parameters. It's like the same definition. We just have n parameters instead of one parameter. The same definition of the operation. We just fix all of them. We can ask to classify these quandles. We didn't eat, but I just formulate the conjecture. And I'm pretty sure that the proof more or less is the same. And the only difference here is in these last cases, where z to the power of n was changed by just a word in this letters. So it's not really important, because if you go to knot theory, then these guys would be useless for constructing invariants, because the group will be the same as with one parameter. So now I understand that my time is going to finish, and my slides also finish. Thank you.
Thank you very much. Any questions? If not, you said that you construct a universal verbal quandle for any group, for instance. Is the question reasonable and interesting if you fix a group and search verbal quandles for some concrete group?
Yeah, I believe that yes, even if we fix not a group but a class of groups, for example, let's say a billion groups. And I believe that there can appear another words which define quandles.
I'm sorry.
No problem. So I believe that the answer to your question is yes. It's interesting. I prefer not to use it. It's useful. It can be useful to fix a class of groups. In my head now, it's a class of a billion groups, let's say, and define, try to find words which define a quandle on, for example, class of a billion groups. I'm sure there will be another, an additional words. And if we recall the start of my talk, why have we do it? In order to construct invariance. And in order to construct invariance, we need, let's say, as much quandles, as much clear quandles as we know. That's why it's reasonable to fix some class of groups and
Yes,
yeah, try to find. So
Thank you. Thank you very much.
Are there any virtual nodes who can prove they had different quandles?
yes, yeah, you just need to paint some picture first. If you want, we can some simple nodes like it, fourth crossing say.
If not, let's thank the speaker again. For 8 minutes before the next one.
Right. Timur, can I ask something?
Of course.
Where
Yeah.
you defender kind of
Hi. Nice talk. So
Thank you.
yeah, so looking at these words that you are getting as in your theorem, so somehow this core and conjugation are sitting there, right?
Yes.
Yeah. So I don't know whether one could say that any verbal quandle with n parameter on each group would be some, in appropriate sense, some deformation of these two standard structures. I mean, core and conjugation.
It seems like seems like it's kind of deformation. We just add z to some power, or I mean a word to some power, and the inverse of this word to some power to some parts of this words.
Yeah,
It's-
exactly.
It's really all of these words look very similar and very similar to conjugation points.
Yeah. Okay. Thank you very much.
about G and three related groups, please.
All right, thank you very much for the introduction, and thank you very much to the organizers for inviting me here and organizing of this wonderful conference. I'm very happy to be here, to speak here. So my talk is indeed about presentations of the gender related groups. And first of all, I'd like to apologize for a slight, let's say, typo in the book of abstracts. So there you can see the title presentations of those groups. That's a mistake. I'll talk about representations. And actually, those groups were already mentioned during this conference, during at least two, well, maybe not exactly those groups, but something like them, during two talks. First of all, during the talk about the generalized Coxeter groups. So G and K in general are an example of those generalized Coxeter groups. And during Valery Bardakov's talk, the groups B and N+1 I mentioned, which are closely related to G N+1 N. So let me begin with seems not to work. Why it doesn't? Oh, perfect. Great, thank you. So first of all, let me describe and remind what those GNK groups are actually. So they were introduced by Vasily Mandrov, and the reason for them, for the existence of them, was twofold. First of all, the idea was to somehow capture the dynamics of the movement of points and points during in some configurational space. And of course, since the groups have two parameters, n and k, there must be something depending on k points, some good enough property. I will describe it a little bit later. And on the other hand, to construct something like a non-rider master braid or knot series. So some theory where the actual moves, the elementary transformations of the objects are not rider master moves, but something different. And it all began with the classical braid theory, and everybody knows, I think, that classical braids may be regarded as a description of some dynamics of endpoints on a plane. So if we have endpoints, they move somehow on a plane, they never coincide, and then we let the time flow from 0 to 1, from 1 to 0, whatever. Then the braid is just a collection of just a world line of this dynamics in the three-dimensional space-time. And when we work with the diagrams of those braids, then essentially what we do, we capture some singularities. So the crossings are singularities, well, in this case of the projection. So for example, if we project along the x-axis, then the crossings correspond to the singular situations when 2 points have the same y-coordinate. And so now if we consider a set of endpoints in some configurational space, for now I don't specify whether it's a plane or whatever, it depends on the task, on the dynamics. And let us fix some number k and consider a property depending on points in this set, which satisfies the following conditions. So first of all, if this property holds for some set of points, and for each smaller set of points, this property also holds. Second, this property holds for every set of smaller cardinalities than k. And finally, the longest property is quite understandable. So if we have a set of k+1 points, then we can take 2 overlapping subsets of k points. And if the property is satisfied for both of those subsets, then for the whole set, it also should be satisfied. So we consider such properties, and if in addition, this subspace of configurations of points which satisfies this property, this fixed property, is large enough, so it's of dimension 1 in the whole, in the total configurational space, then we say this property is good enough for some purposes. And the groups G and K appeared with the following principle in mind. So if we have some dynamics of points which possess this good enough property, depending on exactly how points or particles this language, then the system admits some topological invariant value in this group, in the group Gn. And the axioms, the relations of this group stem exactly from this principle. So we construct those groups so that they give the invariance. For example, the property which we discussed, 2 points have the same y-coordinate, is definitely good. We can just easily check it. So of course it holds, well, if 2 points have, if several points have the same y-coordinate, of course, the small number of them also have the same y-coordinate. Then k minus 1 in this case is just 1, and of course 1 point has 1 and the same y-coordinate. And finally, if we have 3 points and 2 pairs of them have the same y-coordinate, then all 3 of them also have.
Is it related to matroid structure?
I think so, yes. And finally, the space of such configurations is large enough, so it's not a conventional one. And that essentially mean that the dynamics described by the classical braids is closely related to GN2 braids. I'll talk about it a little bit later. And so now let us move to the closer to the gist of my talk. So let's talk about k equal 3. So we have some properties which depend on 3 points. For example, one of the most basic properties of this kind, which I'll be using in this talk, is 3 points lie on the same straight line. So n points are moving on a plane, and at some points of time, 3 of those particles appear on the same straight line. This property is again good. We can check it straight away. And so if we have this dynamics, whenever points I, j, and k appear on the same straight line, we can formally write a symbol a, I, j, k. So those symbols are going to be the generators of our group Gn3. That means, in geometrical meaning, that in the horizontal plane corresponding to this point of time, we have a horizontal, what is called a horizontal trisecond. So a straight line which passes exactly through 3 strands of the braid. I will show a picture in a slide or two. So now, okay. So now let me formally define the group Gn3. Here I don't have in the slides the general definition of Gn-K groups, but it's mostly the same. So we have n choose 3 generators. We denote them A, I, J, K. So those I, J, K are unordered tuples. So for convenience, I will order them in this way. And we have 3 groups of relations. So first group is that each generator is in fact an involution. Second is for commutativity. So if 2 sets of indices do not intersect too much, then the corresponding generators can group. And finally, we have the tetrahedral relations. So they may be described in the following way. Consider some 4-element set from 1 to n. Then we have 4 subsets of cardinality 3, and for each such set, we have this set of relations. Again, since actually those are many relations, because for example, for M1 we can kill any of the 4 elements of the set. And when we talk about Gn-K, the definition is exactly the same. So again, each generator is an involution. We have commutativity, and we have polyhedral relations, let's say, of the same form. One remark which I'd like to make is that if we work with Gn2, what do we have? So second relation is just the usual commutativity braid group. The triangular relation is the triangular relation of the braid group. We know it's connected with the Boxer equation. And the first relation is a little bit unpleasant to some extent, since, of course, in the Artin braid group, the generators are not involutions. We have the difference between a generator and its inverse. But if we talk about so-called free radius analysis of free nodes, where each crossing doesn't have the structure of over and under crossing, then we get exactly this. So each crossing is just an involution. And okay, so here is an example of this horizontal trisequence, which explains what I was talking about. So here we have this braid on 4 strands, and in the language of the GN3 group, we have it described by a word of two generators. So at this point of time, we have A1, 2, 4, because well, we have strand 1, strand 2, and strand 4, and they are on the same line. And at this point of time, we have A1, 2, 3. So this braid is written as 1, 2, 4, 1, 2, 3. But for practical reasons, it appears interesting not to consider just group GN3, but slightly modify them. In fact, in particular, to delete this unpleasant first property, first relation. So forget about the involution. So here we consider a set of ordered triples. So before our generators were numbered with unordered triples ijk, and now the sets are ordered. And now we define the modified tetrahedral relation, where for ordered quadruple of indices, we have exactly this one relation. And now we can define several groups. So GN3 with this small tilde is generated by the set A tilde of ordered triples, and the relations are for commutativity and this special tetrahedral relation for the ordered case. Then we can equip this group with a prime to the left, unfortunately. To the right, we have 3. And that means that we factorize this group by this relation. So we still say that our triples are ordered, but now we do not distinguish between the order of the, let's see, the first and the last indices. Yeah. So J remains in the middle, but we don't care if we have IK or K. And finally, we can consider group GN3 with a hat, which is also factorized, but now we say that now we understand what the inverse generator is. So if we have a generator IJK, then the inverse of it is just the KJR. So inverting the order of the triple inverts the generator. From the geometric standpoint, what those groups are. So GN3 tilde is the most, let's say, global approach. So we have the whole dynamics received all. And we say, okay, we have some orientations of those trisequence. And so at each singular moment of time, we know the order of the indices. So we know at what order the strands go, just like in the usual Artin braids, where we know which strand is closer to us and which one is further from us. The group with a prime, this one, is the most, let's say, local. In what sense? If we look at this singular moment, just a singular moment, we have this line and 3 points, I, J, and K. And we understand then the point J is indeed between the two orbits. But we don't have the orientation of the line. So we don't know if I is the first one or K is the first one. J is definitely the second one. It's in the middle. But I don't know if I have IJK or KJI. So I forcefully say that those two situations are one and the same because I don't have any technique to distinguish them. And GN3 hat is, let's say, semi-local idea when we use the small neighborhood of the singular moment to a little bit distinguish between those two situations, when I is the first point and K is the first point. Again, we don't have the orientation, but at least we can using the information in the neighborhood, we can somehow distinguish them, and that leads to this relation, to this antisymmetry, let's say. Okay, so now I'm ready to talk about representations. And in my talk, there are two approaches to the representing the group. First of all, first part is matrix representations. So the most natural idea is to attribute a matrix of some size, say n by n, to each generator of the group, and then use just the usual matrix multiplication as a group operation. Very most basic idea which exists. And technically, yes, we could just write down a giant matrix n by n, write down a whole lot of equations to satisfy the commutativity and the tetrahedral relation. Yes, here we are dealing for now with the group Gn3 tilde prime, so we don't have the condition. But those matrices naturally are so large that we wouldn't probably get any actual answer, but we honorably die trying. That's not a very good approach, so we simplify our idea and use what is used, for example, in classical representations of atom groups, when we say that our matrices should be of pretty special form. So they are just identity matrices, but some minor, one minor, we replace with something non-trivial. This something non-trivial I call the significant minor of this matrix. So here is the formal notation. What this cumbersome symbol means is that I take basically what I said. I take identity matrix n by n, and then I replace the minor, so columns ijk and rows ijk by the minor m by the matrix m. And for example, we can deal with this group Gen3 prime, tilde prime, work with matrices n by n, take the significant minor of size 3. In that case, the conditions are far easier to check because we can, with the tetrahedral relations, we only need to check for matrices 4 by 4 and the commutativity relations for matrices 5 by 5. In larger matrices, those conditions should be satisfied automatically. Unfortunately, the first step is unsuccessful. This concrete approach, this one n by n with minor of size 3, doesn't give any non-trivial representations of this group. So if we just solve all the equations simultaneously, we won't get anything. Okay, let's try something else, something more sophisticated. We can consider n choose 2 by n choose 2 matrices. What that means? We enumerate our rows and columns not with the numbers of points, but with pairs of points. And the significant minor is still of the size which is 2, so 3. The tetrahedral relation has to be checked for matrices of size 4, choose 2, so 6. And this approach really gives us a nice two-parametric set of representations of the groups G tilde prime. So here is an example. We have several such families, but here's an example. It's pretty simple, but still useful. So the significant minor is of this form where A and D are some parameters, real value. And also for the group Gn3 hat, which is my favorite of those, here we have two significant minors. Why? Because we have to remember that in groups Gn3 hat, we distinguish between their generator and its inverse. So when we work with the generator, we have to work with, we use this m plus minor, and when we work with the inverse, we use the m minus. So they are, again, related, of course. There is some symmetry appearing from this additional relation that A ijk equals A kji inverse But still, this is a nice one parameter family of the representations. And finally, if we try to capture both the direct and the inverted matrices with generators in one matrix. So now we don't attribute different matrices to generators and the inverses, but we try to capture both of them in one matrix. Then we do the following. We consider matrices, large matrices of the size 2 and choose 2 by 2 and choose 2. So rows and columns now are enumerated with ordered pairs of numbers. And so we add two significant minors. So this awful formula means exactly this. We add m plus to the rows and columns ij, ik, jk, and m minus to kj, ki, ji. And again, this gives us now a representation of the group Gn3 tilde. So the very first of these three modifications of Gn3. And here it is, it's two-parametric. Again, the significant minors are somehow symmetric, but now we have these large matrices with two non-trivial minuses. So those are matrix representations. And the second part of the material is to use something like arc actions. So what does it mean? Let us consider a set B of ordered pairs of points for pairs of distinct indices. And let us, for now, equip it with some formal operation star. For now, I don't have any conditions. During a singular moment, we have 3 points ij and k on the same straight line. Again, we still start as the very same special property, 3 points on the same line. And when we look at the small neighborhood of this special moment, of singular moment, we may assume that the points I and j stay on some line, and the third point k moves and crosses this line. And so exactly at the time t0, so all three of them appear on the same line. Technically, since when time moves, ij also move, we technically should say that this line depends on t, but for our purposes, it's not significant. We are considering only small neighborhood of do, and so we may say that it just stays fixed. Okay, so at that moment, we have the generator ijk of the group. And then we say that at this moment, we have action of this element, this generator of the group, on elements of our set B. So here is the action. So aijk acts on ik by multiplying with a star with ij on the right, and it acts on ki, since pairs are ordered, those are different, by multiplying with kj on the right. And other pairs of indices as the elements of B remain. So what does it mean geometrically? When those points appear on the same line, the arc ij, so the segment of this line between I and j, acts on the second segment, not the second, on the long segment, yeah, ik, from I to k, from the first point to the last one, by right multiplication. And likewise, the inverted orientation works, so kj acts on ki. And our representation should stem from constructing a homomorphism from our group to the set of automorphisms of this set B star. So the mapping is defined above. So that's how this mapping works. But of course, for this construction to give representation, we need the operations, the star, to satisfy some conditions. And to no one's surprise, I guess, the theorem states that this section gives a representation if and only if this operation satisfies the rep axioms. And recall that the rep is, as it is said, wreck and ruin left from quandle. So if we forget the idempotency relation in the quandle and only have the subdistributivity and one-sided immutability, then we have a wreck. And those are exactly the axioms which I needed and sufficient for this construction to give representation. And finally, let us deal with group Gen3 hat again. As I said, it's my favorite one, so let's work with it. And let us consider the following quandle-like structure. It's not a quandle in general setting, but it's interesting and important. So let Q be a set with two binary operations, star and slash. And this triple is called a subdistributive medal with right division as DMD for short. If it satisfies the following three axioms, so those operations are actually operation in its inverse, then we have this subdistributivity, and we have this interesting medal condition. So if we have four elements and we multiply I by B, C by D, and then multiply those products, then we can actually exchange the two interior elements. So A, B, C, D is the same as A, C, B. So those are the conditions, relation, the definition of the SDMD. And it is not a quandle, but if we additionally give its idempotency relation, then it transforms into abelian quandle. So, because surely we have those two quandle relations, and we have also this metal condition. This structure is interesting. It's connected to convoy algebras and other constructions in algebra and geometry. So now, how we construct the representation? We consider the direct product of a lot of those copies of Q. So we take and choose two copies of Q and take the direct product. Then we define the binary operations on this product just using the element-wise circle and element-wise slash. Of course, this total construction is also SDMD if Q was SDMD. So then I just remove the primes for simplicity of notation. And also for simplicity of notation, we remove all those subindices and say that Xij in brackets and parentheses is just the collection of all Xij. And subindices are not ordered. So here Xij is the same as Xji. So now each generator Ijk of our group is a hat acts on this giant SDMD in the following way. So if we take the set of x's, then if alpha beta is Ij, it works with a star. If it's Jk, it works with a slash, and otherwise it just remains unchanged. So now we have natural rule for composition, and we have representation. And thankfully, due to the SDMD axioms, this representation is indeed well defined. Why this, in particular, this representation is interesting? This remark and an example shows us. So we already had one representation of Gen3 hat. Remember, with two significant minus, and plus and minus. It's called type 6 with inversion for some technical reason. It doesn't matter now. So if we consider the Alexander quandle, this one is A star B, natural, usual operation for Alexander quandles. Then it is an SDMD, and these, exactly this representation for this partial case of this SDMD gives exactly that very representation which we already. So that matrix presentation is just an example of more general construction appearing from the arc action and from those SDMDs. So I have like 20 seconds left. Let me show some references. So this paper is just the very first place where GNK is appeared those two, the book and the survey, are the most comprehensive, I'd say, works on the theory of group Gen3, which exist now, and with lots of unanswered questions, open problems, and whatnot. And finally, this is the paper which my talk is based upon, so representations of Gen3 and related groups. And that's all I wanted to say today.
Thank you very much. Some questions, comments, please. Could you say if the solution for the tetrahedral equation you presented could serve for constructing two-knot invariants?
That's a question which interests me immensely. Since, yeah, really.
Me too.
Yeah, two knots are currently my main area of study and work. So I do hope so, but I don't have the answer just yet.
Okay. In fact, the algebraic structure of your solution of the tetrahedral equation is very interesting and very relevant to, for example, for the string theory of electrical networks. Do you have some comments about this coincidence?
Unfortunately not. So for now, I just have those solutions, and it's yet to study and to discover how they work in other settings.
And my last question. Sometimes one has a related locally unboxed equation with the solution of the tetrahedral equation. Do you know something related to your solution to the tetrahedral equation?
That's a nice question. I do think that we should have something about that, but I don't think that right now I remember the exact. So I think it's worthwhile to discuss and to look up in our works and to do that.
Thank you. Other questions? Let's thank the speaker again. Have 20 minutes before the next talk of official talk of our conference, and Boris Bishkov will recall us some basic facts from topological recursion and some new results about topological recursion for maps and fully simple maps.
Yeah, so
Please.
thank you. Thanks, Dima. I would like to thank organizers for the opportunity to be on the offline conference. It's a great pleasure for me to speak in real with colleagues. Yeah. Huh?
In life.
Yeah, in life also. So yes, I'm not in Zoom. Okay, and to speak the truth, my talk doesn't fit very well in the main topic of the conference, so groups, quandles, and all-dimensional topology. But so there will be no quandles, but groups and topology will be hidden in this story. But nevertheless, I'll try to overview this so-called topological recursion, what it is, and for what purpose it may be useful. And yeah. So what is about? We solve very simple and clear stated problem. We want to count some geometrical or combinatorial objects, so-called enumeration geometry, and we want to count it and study this counting in different ways. And so, as a model example of this object, which we count, you may think about as about maps as a model example. So map just embedded graph in a surface, in a two-dimensional compact-oriented surface, or equivalently is glue in the surface from polygons. So, and here written something like, so here we have this
So it's an embedded graph.
yeah.
Why it's a map? It's a map.
It's a called map. Yeah, it's called map.
Map in a sense.
Geographic. Yeah. Because of its because of geographical map. So this m, g, n plus m with these all indices is a glue in the surface from n plus m capital polygons, and we fix the number of sides of first n polygons. It will be mu1, etc. And these polygons are distinct. So, and I'll talk about these maps, and also fully simple maps is a little modification of the map. So we require that each vertex is adjusted to at most two edges of a distinguished polygons. So it's a combinatorial condition, which will be very interesting in the side of in the other side of so in the language of generating function, its condition will be very interesting. So this is a model example of what we studied. But so before I proceed with all this topological recursion and later definitions, I want to say a few words why it is interesting to study this for me, to study this enumeration geometry problems. So At first, because of during this research, we use really very different part of mathematics, and today will appear a little of representation theory, a little topology, a little of I could say physics, but nevertheless. And the second, that the methods which arises here also they are very universal. So by methods, I mean this topological recursion procedure. It's very universal, and this means that it covers really very many different problems. So this maps, for example, this maps Gurus numbers in whole generality. Gurus numbers I will not define them, but you may think of it as a number of coverings of the Riemann sphere by a general G two-dimensional surface with some restriction on the ramification profile. So it's Gurus numbers, also some cumulants in matrix models governed by this topological recursion, and it connects with the topological string theory and with Mazur-Rich volumes of holomorphic differential, moduli space of holomorphic differentials, and so on. So these methods are very universal in the sense that they covers very different problems. Okay, so let's continue with definitions. So here, yeah,
it's a formal sum of just of maps.
Yeah.
Not the number of maps.
Uh,
The generating function.
It's so it's enough for focus. Of course, something wrong with written here. Yeah?
The map is a glue.
So we got. So it's a number of such gluons. Yeah. So we're gluing a map in such a way, and we count the number of such.
So some number should be even. Should we do in pairs? Or...
No. So we count weighted numbers. Here you see that I divide by the optimorphism group of this gluon. So yes, and this map capital is a generating function for these numbers. Yes. So here you see that it's a formal definition. So here we sum up all of these tuples of M1 and MP is equal to this M capital and sum over this overall M capital. And the generating function for the simple maps defines analogous. Okay, so and we later I want to discuss this generating functions. Okay, so how it connects with Gurus numbers, which I don't want to define, as follows. So here you see this. Just I'll use it later. These two functions, psi of y and y of z. Here is a concrete function, as you see, and in general case, it may be just a formal power series in y variables. So psi is formal power series in y variables, and y of z is a formal power series, maybe a formal power series in z variable. And this is a so-called k-p-tal function of hypergeometric type. Here, what is written here? So it's a lambda. It's just a partition of. So we sum over all n here, and lambda is a partition of n. And here S lambda is a true function of variables, of these variables. True function, so it's a in variables x, who are these guys. So pk is a power sum in variable x, and in variables x, s lambda is a symmetric function. It's a fraction of two determinants in x variables. It's true function very strongly connected with the representation theory of symmetric group, and the appearance here also because of a connection of all this stuff with the representation theory of symmetric group. But I also skip all this very interesting stuff. And what is written here is exponent in the power of, so we sum overall I and j. We have lambda is a partition, and lambda in the same time is a Young diagram, and I and j, it's just a box in this Young diagram, and we sum up not box, but the coordinates x and y coordinates of this box of the Young diagram, and we sum over all boxes over Young diagram. This psi, again psi is, and here p and t is a formal variables, and here you see this specialization of this second Schur function. It's just because of in the case of maps, y is this concrete z square over 2. Okay, and this is a kp tau function, so it's a connection with the integrable system story due to quite old results of Archer, Konshakov, Morozov, maybe Orlov, Sherkin. And this z, so this z is, as maybe I didn't say, but maybe mentioned that here is written connected or determined because of I want to obtain connected surface. But I also may allow to have disconnected surfaces and connected generating functions, disconnected generating functions. They connect to each other with the inclusion-exclusion procedure on the one side. On the other side, on the side of the generating series, the connected and disconnected series connect with as a if you have a connected series, it's a logarithm of disconnected series, and this equation means that we have this f is a series for connected and z series for disconnected. So it means that the series for disconnected numbers satisfy this identity, and therefore, for example, is a tau function of kp. And so, if in the definitions of the previous slide, this f is this guy, so we have to differentiate this f over p variables, and then put p is equal to 0, and it is this this sum of these maps. And so it is in the case of maps, and in the case of general psi and y, we get what is called general formal weighted double voice. So, okay, it's about some generating series story and definitions of maps and Lorentz numbers. So the next part is how we are working with before I
William, sorry, the Gould's number are related with some particular choice of such function.
so
Just because we
Gould's numbers is so we have a different Gould's numbers. So we have as I said, I didn't say the definition, but Gould's numbers is a covering of S2 by a general G.
so each class of Gould's number correspond to some
Specialization, yes, specialization of psi and y. Yeah. And yeah. And for example, so maps. So it's also you could say that maps is some case of Gould's numbers, but it's like the most maybe geometrical handle example. Okay, so before I start with topological recursion, I want to present the tool which we use to prove and describe all this stuff. It's a so-called Bosonic Fock space. So it's a space of infinite power series, and it's original. It's comes from physics, and the definition of this space is due to boson-fermion correspondence. But I will not speak about it today, of course. And for me and for us today, it's just a space of infinite power series in variables p1, p2, and etc. And we have two distinguished elements in this space. So we have this vacuum vector. It's just the one, and a function co-vacuum vector. It's a function that takes free term of the power series. And I will write the so-called correlators or vacuum expectation values. It's such a guys. So it looks not very pleasant. But if you think of it as a formal power series, and again here we just act. So here we just multiply by 1, and here we just take a free term of this series. Then this vacuum expectation value not very not so huge and looks more or less good. Of course, so here who is this G operators? So here Pi's and Ti's are formal variables. H bar, I didn't say it. It counts the genus of our surface, and except this S2 is also a formal variable, and this J and D, curly D, is are operators in the Fock space. So this G is just this G for positive M, it's this operator, and for the negative M, it's just a variable. And this D operator defines on true functions. Again, true functions, they are functions, they're symmetric functions in X, but if we write them in P variables, then they lies here and lie here, and this D is a diagonal in this diagonal operator in this or in base of sure functions with these eigenvalue. And of course, except of these definitions, I have to define the commute rules of these operators. I also didn't write it here, but together with the commutation relations of these J operators and knowing how to compute this J and this D, curl D, we know how to work with this vacuum exploitation wave. So again, it's not more than just rewriting the generating series in these p variables for counting maps or for counting Hurwitz numbers. It occurs that it happens that this rewriting allows to prove a lot about this generating series. Okay, so this is a huge slide again with notations. What I want to point out from this slide is the this so-called endpoint function. So we had this generating function map, and to speak about formulate topological recursion, I have to have so the topological recursion, for the topological recursion, I have to have rewrite my generating series in the x variables, and so this is the rewriting in x variables, and this is the connection with the previous notations, but maybe I'll skip this part. So because of if there is some mistakes, I think you don't point out, and it's not very important. For us, important that except, so we've had generating series in p variables, and now I want to have a generating series in x variables, just the same generating series, and I'll call it endpoint function because of it depends. We had here p with index mu1, p with index mu(n), and now we have x1, xn in the powers of mu1, etc. Okay, so and what is topological recursion? You may think of it. So you see, we had a huge generating series in these x variables, formal generating series, and you may think of the topological recursion as of some change of variables. So we had this. We have this x small, it is connected with the previous x capital, these guys. And here we have x small and y, it's just the same y that was defined in the first slide. For maps, it's z squared over 2. And in the general case, it's just a formal power series. So you might think of topological recursion as a change of variables. So we had variable x, generating series in variable x, and then we change variables to z, and we have some huge guy in z variables. Also in z1, z2, etc. variables, and it happens that there exists some. There are many, of course, many conditions, but there exists some change of variables that this huge series, that after this change of variables, you can choose some basis in this z in a function on variable z, such that this series will be polynomial in this in this basis. So you might think of topological recursion as some good change of variables, such which allows to rewrite the generating serials in a very rational compact form. And so, but by definition, what is topological recursion? So what is initial data for this recursion? So it's a certain algebraic curve. So usually it's CP1. These two functions again, x of z and y of z, and certain two form. So which lives on the square of the curve. For us, this two form is W02. It's this guy, and also one form will need this guy y dx. It's W01. It's y dx, and this recursion runs for these endpoint functions, but not in variable x, but in variables z, in variable z. Here x z1 means that x1 over z. It's a symmetric differential n form, so that's degree of this spectral curve. And the okay, so the recursion itself, it's this identity, this equation. So here we have this endpoint function with the indexes g and n plus 1, and it connected with endpoint function with indexes with less indexes. So here we have g minus 1 and plus 2, and there this sum is overall partitions of the set z1, etc. z, and all partition of g into two sums. So here exists some condition and some hidden difficulties, but I think I'll skip here. It's just this. So you may think of also of it as this recurrence relations, and so it's diagrammatic or presentation of the topological recursion. So for volumes of modular spaces, it works just as it's depicted here. So we have a genus G curve with n marked points, and here we have genus G minus 1 with n plus 1, etc. But I think I'll also have to skip it. And so that change of variables, which I advertised, it's this one. So x of z is a log z minus psi of y of z, where psi and y is these guys. And in the case of general Gorovitz numbers, generalized Gorovitz numbers, it's this psi and y is just a formal series. So this is maybe the key, not the key, but okay. And after this change of variables, we obtain that the endpoint function are rational expressions, and it's okay. And it's more or less the first result. And this is the theorem. I do not think that it's quite understandable, but as it is. So here I try to depict that we have these polynomials p with some additional guys here. Okay, so it's examples, and the second the second statement that, so you see, I didn't say anything about it, but if psi and y is just a formal power series, it's we're unable to speak about some. So this z, it's a affine coordinate on the spectral curve, and we are working with some function of the spectral curve, and if we have a formal power series, we are unable to speak about some function in the spectral curve. So of course, for the defining of topological recursion, we have to put some analytical assumption on this psi and y, and under this analytical assumptions, this endpoint function. So the procedure of topological recursion gives us the endpoint functions for generalized Gouraud's numbers. So for different choices of psi and y, we obtain all Gouraud's numbers that are known, all types of Gouraud's numbers which are known to this time, and it's more or less the generalize all the work in this area which was before. And the last slide is the third result. It's about these maps and fully simple maps, which are the guys from the first slide. So we have so-called duality between these maps and fully simple maps, and we state that if we know the topological recursion for one side, we obtain the topological recursion with another side. It's another interesting story because of here appears the vacuum expectation value for the fully simple guys. It's different from the ordinary Gouraud's numbers case. We have here this d minus, and yes, okay. So I have to stop here, I think. Thank you.
Any questions, comments? If not, however, to be honest, to say something about the title of the conference, is there some version of such generating series who says something about nodes on surfaces?
Yes. So I have to mention, of course, that also this topological recursion governs Hoppokamur-Waf invariance for torus nodes. It also fits this topological recursion procedure.
So there is some dual spectral curve which governs such kind of things. Very interesting. Other questions? Let's thank the speaker again. If you say something.
Да, с удовольствием, если можно уже по-русски. Да, значит, это был последний доклад из последнего заседания. Я очень признателен всем докладчикам этой конференции, всем участникам. Я надеюсь, что доклады были интересные, дискуссии были полезные. И я думаю, что зародились какие-то новые идеи, там, контактов. Я знаю, что некоторые вещи были сделаны в течение этой конференции. Вот я думаю, да. Я надеюсь, что вам понравился Tomsk летом. В случае тех, кто не был летом. Я надеюсь, что мы продолжим эту серию конференций. По возможности, конечно, мы приглашать иностранных докладчиков тоже. Раньше проводили все вживую, сейчас так не приходится делать. Вот. Большое вам всем спасибо. Если какие-то есть там пожелания, вопросы, то я думаю, что сейчас просто уже не осталось ничего этой конференции.
Да, организатор, да.
Андрей, пожалуйста. Спасибо большое.
Спасибо.
Так, расскажите, что вы сейчас делаете? И завтра тоже, да?
Сегодня в 12:30 Бонапарта будет автобус. 16:30 автобус будет обратно.
16 ты все равно туда поедешь.
16:30.